I try to talk louder. We wait a couple of minutes, and I already started to share my desktop, so if you have troubles, we wait other 3 minutes before starting to see if other students in the meanwhile will come. I start recording. Okay, I talked with Ilaria Tamburini, and I talked about your courses, the course of energy and something else you told me. I think, no, she told me that she thinks Ben had the same problem the first day, and this morning before giving you the link here. Well, however, she told me that she will see tomorrow. I also told her to ask you. I don't know how she can contact you, but I think she can take contact with you to say what's going on if you have troubles with the room, so you can explain her the problems you are facing. So guys, I think no other student will come, so 26 we are, but maybe other will come, but they will spend all the time they need. But now we need to start. Okay, so we continue with descriptive statistics, and in particular we are going to see the last topic of descriptive statistics, which is the regression line. So here in this case we are going to describe only the regression line. The linear regression model will be discussed in one of the last lecture of this crash course. So for the moment I simply introduce the regression line, not the complete regression model, but only the regression line. Because today we talk only, at least today, in this presentation we talk only about the first field of statistics, which is descriptive statistics, in which, given the information provided by your sample, you try to get some indicators, and you want to try to summarize the information provided by the sample you have. So suppose you are in, again guys, if you have troubles, if you have troubles, if you have question, you can turn on your microphone, and so you can stop me. In particular, guys, we read together. Suppose you are interested in studying the relation between income and consumption for a group of n families. We have already seen before how to measure the degree of linear dependence between two variables. In particular, we saw the sample covariance and a normalized version of the sample covariance, which is the sample correlation, which is an indicator that assumes a value between -1 and 1. However, we want to go, when I explained correlation, I told you that when I explain linear correlation, yes, when I explain linear correlation or the covariance, I told you that the direction of the dependence is not specified. You don't know if x depends on y or y depends on x. is because covariance of xy is equal to covariance of yx. Correlation of xy is equal to correlation of yx. Now we want to go on, and we have always in mind this sort of linear relationship between two variables. Let the consumption and the income of a family in the sample. Okay, x, for example, this is the sample containing the income of the capital N individuals. This is a sample containing the consumption of the same N individuals. And as I told you before, the pair xi, yi can be used to represent the ith individual in a system of Cartesian axis. In particular, xi is the observed income of the ith family, and yi is the income of, I told you the contrary, xi is the income of the ith family, yi is the consumption of the ith family in your sample. So suppose that this is, I want to represent this sample, what's going on here. Suppose, guys, you want to represent the sample, in this way, that is plot, so each point corresponds to an individual. This graph, this one, is called scatter plot. So each point, as you can read, so you don't have to add nothing, represent a particular individual. So in the axis of a point, you read what? In the axis of a point, you read the income of the family corresponding to that point. As a vertical distance, you read the consumption of the family corresponding to that point. The idea is the following. So here we have n, which is the total number of points. The idea, which is typically, guys, what do you think? Typically, which suppose you want to express one of the other, one variable as one of the two variables as a function of the other to describe the relationship in the sample between the two variables. And in particular, suppose you assume you want to model this relationship through a linear function. Remember, guys, first of all, if you want to, so guys, which is a linear function? Remember, I wrote it last year, so I don't know if you will see. This means is, remember, we studied the first day of the crash course of mathematics, the straight line. So y equal to mx plus q is the equation in mathematics of a straight line. M is the slope, q is the intercept at the origin, x is the independent variable, and y is the dependent variable. So guys, what do you think? Suppose that we want now to express one of the two variable as a linear function of the other. So what do you think? Do you think that it makes more sense to express the income as y as a function of the consumption, or to express the consumption as a function of the income? Obviously, it does make sense to express the consumption as a function of the income. So we want to estimate, guys, this straight line, but this is a mathematical straight line. We want instead to estimate, given this point, the straight line in which y is the consumption, is the dependent variable because depends through x, and the other one x is the independent variable. So guys, again, this is a mathematical relationship here. Okay, we studied it, perfect straight line. Now we want to find the straight line that best represents our points. That is, you want to find the best straight line that can be used to approximate the relationship between the income and the consumption for the family in our sample. So, and in particular, in statistics, this line is called regression line. I want to show you how to get the regression line. We will discuss with more detail, as I told you at the beginning of this lecture in the afternoon, about the linear regression model in the future. So for the moment, I simply explain it in general and I give you some result. The regression line is the straight line that best fits the data. This line is also called OLS. O stays for ordinary, L stays for least, S stays for square, because the equation of the straight line is obtained by solving the so-called OLS problem. I will explain here in a moment. Okay, here I reported the problem, but let me explain before by doing through the graph. I think I did. Okay, look at this graph, guys. Look. Guys, who is here? Who is need to come? Guys. Okay, guys. So, look at this straight line, guys. Okay, sorry, this is, look at this point, first of all. This point represents our scatter plot. So, this point represents the individual in our sample. We want to find the line that best fits our data. Suppose that the line is this one. Suppose that the line is this one, and we want to estimate a straight line. Guys, to estimate a straight line, what do you need? In mathematics, you need to know the slope, which is m, and the intercept at the origin, which is q. Okay, so however, in mathematics, I have shown you how to get the equation of a straight line when you have 2 points, because through 2 points only a straight line passes. Here instead you have a lot of points, and obviously you cannot get a straight line passing through all the points. So you want to find the straight line that best represents our data. So how can you do that? How can you do that? How can you do that, guys? So reason with me. Consider this point, the one I'm touching. The one I'm touching, and go below. Go below, go below, go below. Suppose that, which is the axis of this point? The one I'm touching, guys. I try to do in red. Which is the axis of this point? Call it xi. Xi. So is the income of the ith family in your sample. Which is the consumption of the family in your sample? Is this vertical distance. So you can go horizontally here and here. This vertical distance is the consumption of the ith family. However, suppose you estimated this straight line as the straight line that best represents in your sample the income as a function of the consumption, which is the value given xi, that is given the income of the ith family, which is the consumption predicted by using the straight line. Guys, you have simply to evaluate the straight line at this point, at xi. So suppose that, go vertically here, and the point is this one. This one. So you have the point here, go vertical until you touch the straight line. If you read horizontally, this new vertical distance, this one is the consumption for a family with an income like the one of the ith family. So you see that this is the predicted consumption, okay, or the estimated consumption through the estimated straight line. So you see that you are committing a mistake if you estimate the through consumption with y hat high, because which is the effective consumption of the ith family? Is yi, is the vertical distance. Instead, y hat I, this shorter vertical distance, in this case, is the predicted consumption level for a family with an income equal to xi. So consider this vertical distance, the difference between y high and y at high. Let me see if I use this notation above. Yes, I use the same notation, so let me show. yi, which is the effective consumption of the ith family, minus the consumption for the ith family, or in general for a family having the same income of the ith family, is y hat I. The difference between the effective consumption and the predicted is called residual, which is the mistake we commit if we estimate yi with y hat I. So EI is the residual, is essentially simply, guys, yi minus y hat, and it is this vertical distance. Okay, so which is the expression of y hat I? We assume that in the sample the y's can be expressed as the function of the xi's. Okay, so let me see. So go here. So y hat I, according to our straight line, will be given by what? By the estimated intercept. We called the estimated c-intercept, that is m, the estimation of m, as beta hat 1. So beta at 1, which is the slope of the estimated straight line, times the consumption of the ith family, plus the estimate of the intercept. This is, guys, plays the rule of Q, okay? So this is straight line. So you see that yi at is a linear function of xi. So the function is this one. Okay, this is the linear function. So the slope of this straight line is beta hat 1, beta hat 1. On the contrary, the point of intersection here, okay, the intersection is almost at the origin, but in general, the point of intersection of your straight line with the vertical axis is the point 0, beta hat 0. So beta hat 0 is the ordinate at the origin of the point of intersection of our straight line with the vertical axis. So here I wrote yi hat equal to beta 0 hat plus beta 1 hat xi. So this is the estimated or predicted level of consumption of the ith family given its level xi of income, because if you know the income, if you know this number, you know the income, you can predict automatically the value of the consumption for the ith family using these linear relations. So which is, guys, the residual? The residual is yi minus y hat I. We can substitute into y hat I its expression, so we can write the residual in this way: yi, the effective consumption, minus beta 0 hat minus beta 1 hat times xi. So which is our goal, guys? Keep in mind that we want to find the regression line. The regression line is characterized by this, which is the estimate of the intercept, and this, which is the estimate of the slope. So we want to find, I repeat, the straight line such that we say that the errors committed by approximating all the yi with all the yi hat is minimized, is smaller as possible. Okay, so, and to find this straight line means that we need to find this constant and this constant, the estimate of the intercept and the estimate of the slope. Okay, so here, guys, essentially I wrote everything. Guys, and now reason wrongly with me first. So we want to solve this mathematical problem, which is a problem in two variables, and you will study with Roberto Dieci in mathematics optimization of function with more than one variable. You studied already with me optimization, you reviewed with me at least optimization of function with one variable. Here instead we want to minimize this function. Look at this function. It's the sum from I equal to 1 to n of what? How many observations, how many individuals do we have? We have n individuals. So you have yi minus yi hat, which is the error. For the moment, neglect the 2. Forget about the 2. Don't cancel it, but forget about it. So what is this formula without the 2? Is the sum of all the residual E1, E2, E3, E4, E5, etc., etc. That is the sum of all these vertical distances between all the points and the horizontal and this straight line, the straight line that we want to find. So the EI, the sum of the EI is the sum of all these distances. But wait a moment, guys. This is a function, okay? This is a function. I stop here because we'll explain it also better in one of the last lectures. But here, what you have to do, guys, you have to insert the expression of y hat I. Which is the expression of y hat I? Here, guys, I explained everything. This is. So you have essentially to put inside parentheses this quantity. You can see, guys, that the ith error depends on beta 0, beta 1 hat, yi and xi. E3, the third error, will be equal to y3 minus beta 0 hat, beta 1 hat, x3. So what I'm saying is that for all the n observations, that is, for all the n residuals, E1, E2, etc., etc., En, you see that every residual depends on both beta 0 hat and beta 1 hat. So I repeat, so the trick, we want to find beta 0 hat and beta 1 hat such that the sum of the residual, neglect for the moment this one, the sum of the residual is minimized, but you see that y hat I, as I shown you before, below, just 1 second ago, depends on beta 0 and beta 1. So what I'm saying is that you know the yi, you know the xi, the unknown of this function are beta 0 and beta 1 hat. So this is a function, guys, that depends only on 2 variables, beta 0 and beta 1, which are unknown. So we want to select the best combination, the combination of beta 0 hat and beta 1 hat that minimizes this function. We know what does mean minimize the function. It means that we want to find the global minimum if it exists. And we studied global minimum, global maximum, etc., etc. The only difference with respect to what we studied together is that when we studied, we minimized the function of one variable. So, for example, minimize this function with respect to beta 1. On the contrary, here we have a function of 2 variables. Okay, this will be explained by Professor Dieci in mathematics. However, important thing is you understand that we want to minimize this problem. However, am I really right that we need to minimize this sum by neglecting the square here? Look below. Does it make sense to find beta 0 hat and beta 1 hat by minimizing the sum of the residuals? Look with me. Go to the picture. Well, you see that this residual is positive. This residual is positive. This is a residual positive, so it's good. However, you see that you have also observation or individuals below the horizontal, below the straight line. So, for example, this mistake, this vertical distance is negative. This vertical distance, oh, sorry, my partita, I did it too long. I want to say, no, cancel this one. I'm saying only this part, okay, this short part, this here, this part here are negative residual. So, guys, when you sum, if you minimize the simple sum, you have that, guys, you may in theory have very huge mistakes, but a very small sum of the residuals. Why? Because you can suppose you have a point here and another symmetric here, a point here and another symmetric here, and a point here and another symmetric here. If you suppose that all the points above have also a symmetric below this line, in this case you would have that the sum of the residual is equal to 0. But this does not mean that your straight line is good. Why? Because you have a lot of residuals. So which is the problem you have in general, guys, if you minimize the sum of the residuals? Is that positive and negative residuals tends to compensate each other, making small the total mistakes, the sum of the residuals. So to avoid this problem, we minimize the sum of the residuals, each one taken to the power 2. Why? Because if you have a positive huge residual or a negative in absolute value huge residual, the negative has the same weight of the huge positive. So what I mean, all the residual now, all the mistakes have a contribution in the function. So bigger the mistakes, bigger the value of the function. Instead, if you consider the simple sum of the residual, negative compensate with positive. If you raised to the square, all the residual taken to the power 2 are positive. So more the residual, more the sum of the square. So the principle is the following, and then I stop here. We need to minimize this function with respect beta 0 and beta 1. I stop here, because this is a mathematical problem. You have to compute the partial, okay, I stop. Partial derivatives, etc., etc., etc. For the moment, I stop. Okay, so by solving the problem I told you, guys, by solving the problem I told you, please here, please guys, wake up if I make you to sleep, because by